Hello everyone and welcome back to Shocked Up. I know it's been a little bit of a while since we've uploaded any new content due to the hectic holiday season and first semester, but I thought we'd kick off this semester by showing you guys the projects I've been involved in and the videos I've created in the previous semester. And if you guys have any questions about the systems I'm about to show you guys, just feel free to leave a comment down below and maybe we can touch on it in a future video. So first off, we have the concept of a bidirectional electric vehicle charger. This system is supposed to be smart enough to charge the electric vehicle during off-peak hours, which is when the cost of electricity is low, and discharge the electric vehicle's battery back into the grid when the cost of electricity is high. Therefore, it can eliminate the overall cost of charging an electric vehicle at your home, along with several benefits on the distribution side. With the market for electric vehicles continuously rising, local distribution companies and the grid will struggle to meet the power requirement needs necessary to charge electric vehicles during peak hours. Therefore, it is critical to think of a solution now to ensure the reliability and integrity of the grid. Therefore, we developed a prototype of a standard bidirectional electric vehicle charger, which is capable of using a time-based algorithm to control the power flow from our electric vehicle to the grid. So here we have our electric vehicle, which is symbolized by this battery pack, our bidirectional electric vehicle charger, and our lamp, which symbolizes the grid. So this charger, by utilizing its time-based algorithm in which 1 hour is equal to 3 seconds for this demonstration, it is able to control the power flow based on time. Therefore, during low peak hours, it is able to act as a standard battery charger which charges our electric vehicle. And during high peak hours, it can inject power back into the grid, which allows our electric vehicle to act as a spinning reserve to lessen the load on the grid during peak hours and reduce the strain on the grid. Another feature of this electric vehicle charger is its power outage generation capabilities, in which if a power outage occurs, which is symbolized by me disconnecting the charger from the grid, it is able to kick on a backup generation unit which can island you from the rest of the grid and power your house during an outage. Therefore, you'll never be affected by an outage again. So next off, we have the concept of a high-power wireless power transmission system, which is to be incorporated into the bidirectional electric vehicle charger. This way, the bidirectionality between charging and discharging between the vehicle and the grid can occur wirelessly. Phase 2 of our wireless bidirectional EV charger involves incorporating the wireless charging and discharging aspect into the prototype shown before. So utilizing this circuitry in front of me, we're able to power a load such as this LED wirelessly through these induction coils. And as you can see, as the coils come closer together, the LED lights up. And just to show, it can even power the LED through a surface. And this method will be used in the charging and discharging of our electric vehicle wirelessly. This system will be utilized in both the electric vehicle and the car charger to be able to transfer power wirelessly through one another using our time switching algorithm, so we can power various different loads wirelessly, such as this electric motor. So breaking down the system, first we have our signal generation unit. Our 555 timer creates a square wave with an amplitude of 5 volts and a frequency that's tunable with this trimmer potentiometer, and we tune that to the maximum Q value of our induction coils, which is 160 kilohertz, to ensure the highest power transfer between our coils. That signal is then fed into our MOSFET drivers. The signal is also fed into our inverter gate, which creates the opposite square wave at the exact same frequency, which is also fed into the drivers. So to show you our two opposite signals from our 555 timer and inverter IC, we have it drawn here on the board. So as we can see, our 555 timer outputs a 160 kilohertz signal with an amplitude of 5 volts, and our inverter IC does the exact same thing. Only if we take a closer look, we can see that these two signals are complete opposites. So when the 555 timer outputs 0 volts, the inverter will output 5 volts, and when the 555 timer outputs 5 volts, the inverter will output 0 volts, which will give us our two opposite signals. Our two opposite signals from our 555 timer and inverter gate are then inputted to our MOSFET drivers, which maintains the exact same frequency but amplifies the 5 volts to 12 volts, which is a usable voltage for our H-bridge. Our H-bridge is comprised of 4 MOSFETs which receive the signal from our MOSFET drivers as well as a high power DC voltage, and then creates a high power 160 kHz signal to our transmitting coil. So here we have a close-up of our 4 MOSFETs in an H-bridge configuration. Our 2 separate signals come from our MOSFET driver, which takes our inverted and 555 timer signals and amplifies the 5 volts to 12 volts for our MOSFETs. So when signal 1 goes high, it turns on our MOSFET 1 and 4, which allows current to flow from VCC through the coil in this direction to ground. And when signal 2 goes high, it allows the current to flow through MOSFETs 2 and 3 in this direction to ground, which creates our alternating current through our transmitting coil. The high power 160 kHz signal from our transmitting coil is then received by our receiving coil, with which the signal then gets rectified into a DC voltage to power any load. So thank you for watching these demonstration videos. We hope you enjoyed them, and we look forward to bringing you phase 2 in the future. And lastly, we hacked into a standard remote control toy car using an Arduino, and using MATLAB, we're able to distinguish between voice commands to get the car to actually run off of voice commands alone. So before I show you the video, the natural heading of the car is 0, which is why in the video you'll see when we say 90, the car will turn right, and when we say 270, the car will turn left. Forward. $270. $90.
And then
Back.
we only load one of those files. We load the 3 one. We load everything. To the same
270.
folder of the script of the MATLAB. So we'll have a folder that has everything. Let's see.
90.
Then we have to pick the exact file that we want to read.
Yeah, that's in the MATLAB code.
So that's everything for this video. My apologies in the first 2 videos where I was wearing a white dress shirt if I look like I'm dying, but those videos were recorded at 5 a.m. and I was running on minimal sleep during that period of time. So my apologies for that. But if you guys have any questions, like I said, feel free to ask away, and I'll try and answer it, or I'll make a follow-up video describing the systems in a little bit more detail. As always, don't forget to like, share, and subscribe, and follow us on Instagram so you're the first to know when new shocked up content is released, and we will see you next time.